Picture the universe right after the Big Bang. A fraction of a second in, it was a hot, dense plasma full of tiny density differences from quantum fluctuations stretched by inflation. In overdense spots, theory says those pockets could collapse straight into black holes. We call these primordial black holes. They formed before any stars lit up, maybe 100 to 200 years later. If enough of them paired up and merged across billions of years, they would send out gravitational waves. These would show as faint ripples in spacetime that reach us now. Some researchers talk about these as dark sirens, signals from the invisible time before light filled the cosmos. Most astronomy uses light. Telescopes collect photons from stars and galaxies to build pictures of what we can see. Gravitational waves give us something different. They let us sense distortions in spacetime caused by massive objects in motion. Pulsar timing arrays, like the one run by NANOGrav, turn the galaxy into a giant detector for these low-frequency waves. They monitor millisecond pulsars, neutron stars that spin incredibly fast and send out radio pulses like extremely reliable clocks. When a gravitational wave passes between Earth and one of these pulsars, it stretches or squeezes spacetime along the path. That tiny distortion changes the travel time of pulses by a very small amount, often just microseconds or less. By carefully measuring the arrival times over many years and looking for patterns that show up the same way across different pulsars, researchers can spot a shared signal. That's how NANOGrav's 15-year dataset revealed a stochastic gravitational wave background, a steady nanohertz hum made up of many overlapping waves from distant sources. In February 2026, their latest analysis took another step forward by mapping out potential individual candidates for merging supermassive black holes. This all connects to a real puzzle about the early universe. Some models don't quite account for how much compact mass or how quickly structures formed back then. The pulsar data keeps primordial black holes in the conversation as a possible piece of the puzzle. Maybe their mergers or the waves triggered by their formation in those early fluctuations add to the hum we detect. This could help explain why the infant cosmos seems to have been more densely packed with objects than certain predictions suggest. The way these arrays actually pull out a real signal is pretty clever. Researchers collect years of precise pulse arrival data from pulsars all over the sky. Then they look for tiny timing shifts that aren't random. The key is finding shifts that match up in a specific way across different pulsars, depending on their positions in the sky. General relativity predicts exactly what that pattern should look like for gravitational waves coming from far away. This is called the Hellings-Downs correlation. When you see that distinctive pattern emerge from the noise, it points strongly to a gravitational wave origin rather than something local or individual to one pulsar. Pulsar timing arrays are excellent for the very lowest frequencies. But to go higher, into the millihertz territory, we'll need something in space. That's where LISA comes in. It's planned as 3 spacecraft flying in a giant equilateral triangle formation, each side about 2.5 million kilometers long. They orbit the Sun along a path very similar to Earth's own orbit, but the whole triangle trails behind Earth by roughly 20 degrees, about 50 million kilometers, so it stays far enough away to avoid interference from our planet. Lasers bounce back and forth between free-falling test masses inside the spacecraft, measuring changes in the distances between them with incredible accuracy. In January 2026, engineers at NASA's Goddard Space Flight Center completed tests on a second prototype of the frequency reference system. It is identical to the first unit tested back in 2025. These checks confirmed the system's stability and ability to keep the lasers precisely tuned and synchronized over those huge distances, a crucial step toward making the full mission hardware flight ready. The level of precision LISA is aiming for is on another level. It needs to spot changes in distance smaller than the width of a proton across millions of kilometers. Think of it as measuring the distance to a nearby star with an accuracy finer than a hair's thickness. With that kind of sensitivity coming online in the 2030s, LISA will open up a whole new part of the gravitational wave spectrum. That's the millihertz band that pulsar arrays are not as tuned for. This higher frequency range lets us hear signals that have been shifted or stretched in different ways over cosmic time. We will pick up a steady background hum from lots of overlapping distant sources that blend together. That gives us a statistical picture of what is out there. At the same time, it should provide much clearer snapshots of the individual events. That includes those from far back in the universe's history, where redshift has moved their waves into this window. Now that we have detectors tuned to different parts of the spectrum, the next question is what the signals themselves actually look like. If primordial black holes were merging and contributing to what we detect, their waveforms would not resemble the sharp, sweeping chirps we see from nearby stellar mass black hole binaries in ground-based detectors. Those nearby events produce a clear upward glide in frequency as the objects spiral closer and finally merge. Primordial mergers, by contrast, would tend to blend into that much smoother, more continuous contribution across a broad range of low frequencies. The reason is simple. Their masses could span a wide range, from objects lighter than the Sun all the way up to hundreds of solar masses, depending on the size of the density fluctuations that collapse to form them right after inflation. That mass spectrum is important because it directly reflects the conditions in the very early universe. The scale and amplitude of those primordial density perturbations set the sizes of the black holes that could form. When we look at the low frequency ripples that reach us today, cosmic expansion has stretched them over billions of years. This redshift lowers their frequencies and leaves a characteristic imprint on the overall shape of the spectrum. It's like a fingerprint that tells us how clumpy and uneven the infant cosmos really was. The advances of LISA's hardware, including the confirmed stability of the frequency reference prototypes from 2026, help tighten the sensitivity in the millihertz band. Better laser control means we can set stricter limits on what signals are present, and separate their faint features from stronger foreground noise, such as the gravitational waves produced by countless white dwarf binaries in our own galaxy. While the nanohertz background we see with pulsar arrays aligns most closely with supermassive black hole binaries in merging galaxies, theoretical models continue to test whether primordial black holes could explain parts of the signal or related features. The real power comes when we stop focusing only on individual mergers and start listening to the collective hum. This overlapping background is not just noise, it is a statistical map. It reveals the overall distribution of sources across cosmic history and gives us clues about the turbulent process that shaped the large-scale structures we see today. The real insight from this overlapping gravitational wave background comes when we treat it like a form of cosmic sonar. The ripples travel through space and interact with mass along the way. In doing so, they can outline distributions that light alone cannot reveal. If primordial black holes were present in meaningful numbers, their positions and mergers would trace patterns in dark matter. They could mark out clumps or even contribute directly to some of the invisible mass that holds galaxies together. One of the most intriguing ideas is that primordial black holes served as the original seeds for supermassive black holes. Start with a small black hole formed in the early universe. Over billions of years it grows through acceleration of gas and stars, plus mergers with other compact objects. Eventually, it becomes the massive central engine we find in nearly every large galaxy today. This seeding mechanism helps explain why supermassive black holes appear so early and so large in James Webb Space Telescope observations of distant galaxies. The background hum provides indirect evidence by showing the abundance and distribution of compact objects across cosmic time. Recent refinements in pulsar timing data, including the 2026 analysis, that map more individual candidate sources, support models where the early universe was packed with more of these compact objects than many standard simulations assume. That implies a more active and violent phase of structure formation, more frequent interactions, more rapid growth, and a cosmos that assembled itself faster with greater intensity than some theories once predicted. This perspective changes how we think about the signals. They are no longer just detections to catalogue. They become preserved archaeological artifacts. Each ripple carries information from the formative stages of the universe. By studying the collective background, we reconstruct the conditions and process that shaped everything from galaxy clusters to the large-scale cosmic web we observe now. If even a portion of this gravitational wave background turns out to include contributions from primordial black holes, it would extend our view of cosmic history all the way back to the end of inflation, and the first fractions of a second after the Big Bang. That kind of reach would place tighter constraints on theories of gravity, the physics of the very early universe, and the processes that led to galaxy formation. We would gain a clearer picture of how the large-scale structure we see today emerged from those initial conditions. The hardware progress of LISA in 2026, particularly the successful frequency reference prototype tests that ensure laser stability over vast distances, is laying the groundwork for millihertz observations in the 2030s. Combined with continued improvements in pulsar timing arrays and potential future ground or space-based detectors, the coming decade should allow us to resolve finer details in the background. We may even push our effective listening back toward the literal first millisecond of the universe, testing models of cosmic inflation and quantum fluctuations at scales we have never probed before. If this burst of curiosity was useful to you, more will follow on the channel in time. Sláinte.